Hi everyone, welcome to this new lecture of fluid mechanics. In this lecture, we'll discuss the equation of force vortex flow. In our previous lecture, already we have discussed the generalized equation for the vortex flow, and now we'll see the equation for force vortex flow. So already we have discussed what is vortex flow and what is force vortex flow and what is free vortex flow. Now let's derive the equation for this force vortex flow. So we already previously know that when the liquid will be circulated or it will be flows or it will be rotated, there will be a vortex creation will be there. That means when the liquid flows will be there, either it may be in the sink or it may be in the pipe, bent pipe, or in the pump or in the turbine, then there is a chance of there to form a vortex. Okay, and that vortex formation also, maybe it can be naturally formed or it may be forced, maybe. So which is formed with the help of force, external some source, then that we used to call as a force vortex flow. So let derive the equation for this force vortex flow and see what the equation is coming out from this. So for this, I have taken two diagrams here. This is one diagram and this is another one diagram. Okay, so before going to this diagram, let me remind you what is the equation for the force vortex flow. So we know that the force vortex flow, actually we know that V equal to omega into R. So this V equal to the velocity of the liquid, and this is angular velocity and the radius of this liquid which is present from this. If this is the axis line of this liquid, and the after rotation, what is the point we are taking consider from this center line? Suppose if you take a second point, then this is a distance of R2, and this is suppose point 1, you can consider R1. So similarly, we have seen already in our previous lecture already we discussed what is the velocity equal to this angular velocity into R. And here the angular velocity is equal to constant. This omega equal to, this is constant. Okay, and we also know that another one equation we got in the last class, if you remember in the last lecture. So that is the pressure variation equal to del P equal to rho V square by R into dr minus rho G dz. If you not remember or if you have not seen the previous video, let me remind you, this is the pressure variation or variation of pressure of a rotating fluid. Okay, this is the pressure variation of a rotating fluid. Okay, this is in terms of this is from the hydrostatic law, and this is, you can say, in the vertical direction, and this is in the horizontal direction, rotational condition. That's why we got this equation in the previous lecture, and this is actually generalized equation for the vortex flow. Now we are going to discuss about the force vortex flow. So what we'll do, let put this value of this V in this equation. The V value means the force vortex flow equation. Let's put in this generalized equation. Okay, so once you put the value, then what we'll get here, we'll get del P equal to, you can get rho, in place of V, let's put omega R. So we'll get what? Now omega square R square by R into dr, and this is as usual rho G and dz. Okay, now this is equation what we got from the force vortex flow in this, from this general equation. Now let's consider 2 points are there in this diagram. If you see point 1 and this is point 2. So these 2 points in the fluid are having the force vortex flow, because after rotation of this shaft, this vortex formation happened. Okay, this is the vortex formation happened after the rotation. So here let's consider a point 1 and point 2. Okay, which is in the force vortex flow. Now let integrate this equation with respect to this 1 and 2 location. So if you integrate this equation, then what will happen? Like integration 1 to 2. Similarly, here also integration 1 to 2, and here also will give integration 1 to 2. Now, if you integrate integration of dp, we'll get p, and that integration of p, the limits 1 to 2, what will get? That will be there, upper limit minus lower limit. Similarly, here also we can get, integration this one. We will take a few terms outside. So that means omega, let take it outside, and omega square rho outside, r square by r. That means r will be cancelled here, and 1 r will be there, r dr, integration of r dr, that is r square by 2, r square by 2, and this is the limit we can give 1 to 2. And next is similarly minus of rho g dz. Okay, so that will be there, rho g will be constant. Let's take it outside of the integration of del z, dz into 1 to 2. So that will be, we can write rho g bracket start z and the lower limit 1 to 2. Okay, now again we can write this equation p2 minus p1 equal to, we can write rho omega square and bracket start, let's write r2 square minus r1 square. Just say put the value of this upper limit lower limit in the r. Similarly, here also we can put it rho g, and this is z2 minus z1 bracket close. Similarly, we can write again the value of omega r. Let put the value omega inside. Okay, so what will be there? p2 minus p1, and this is omega rho, and here bracket, let's start omega rho by 2, keep it here, and here we can write omega square r2 square, and this is omega square r1 square, this is bracket close. Similarly, rho g, and this is z2 minus z1. So here we can give a normal bracket on behalf of square bracket. It is already over, so we can give normal bracket. Now you see omega square r square, we already know that omega r equal to v. So here we can write what? Now rho by 2, here we can write, let's write this v2 square minus v1 square bracket close, and similarly rho g into z2 minus z1. Okay, because we know that our v equal to omega into r. So we got this equation like, this is the pressure difference what we got like in p2 minus p1 equal to here rho by 2. Yeah, let me give a bracket of this p2 by p1. Okay, now we got this equation. Now that now here we can take this condition, the point 1 and 2. This is the point 1 and this is the point 1, 2. Now if the point 1 and 2, if lies in the surface of this vertex, okay, in this liquid, the vertex which is created here, if it is lies on this liquid surface, in the surface of this, okay, then what will happen? Obviously, if you see here, the pressure differences are there when we are considering in the inside the liquid, because we know that as per the hydrostatic law, we have, if you go deeper, you will have the pressure will be changed. Okay. Now, if both the points are situated on this same layer, then what will be the condition? At that condition, what will be there? Now, our pressure P1 and P2 both will be same. Okay, there will be no difference in the pressure. So if P1 and P2 are same, then the equation what we can write, now P1, P2 minus P1 was there, so that will be 0, and we can write rho by 2 bracket start, this is V2 square minus V1 square bracket close, or you can give the normal bracket also, rho g, and this is Z2 minus Z1. This is also you can give normal bracket. Okay, now similarly we can write again, this is 0 is there, let's take one term in this side and one term there, so that means rho by 2, this is V2 square minus V1 square equal to rho g Z2 minus Z1. So you can write what, rho we can cancel, and here you can write Z2 minus Z1 equal to 1 by 2g. Let rho g this take it this side. So the rho cancel. So 1 by 2g into V2 square minus V1 square. This is the equation what we are going to get if the point 1 and point 2 both are lying on the surface of the liquid. Similarly, if the point 1, let's consider a point 1 lies on the axis of rotation. Okay, let's consider the point 1 which is lying on the axis of rotation, suppose axis of rotation. Then in that case what will get? In that case what will get? Now V1, what do we know? Omega into R1. So here there is no distance of R because it is lies on the axis of rotation. In the same point, axis point it is locating. Suppose this is the axis is there. Okay, in this axis point the point 1 is lying. Okay, then there will be no distance of this, R1 will be not there. So very simple. So R1 point will be 0. R1 0 means this V1 will be 0 here. So in this case what we can write this? We can write Z2 minus Z1 equal to 1 by 2g. This V1 square part is 0. Only we can write V2 square, or we can write this Z2 minus Z1 equal to V2 square by 2g. Now this Z2 minus Z1, if you just to mark it as a capital Z, okay, so we can write capital Z equal to here V2 square by 2g, or if you want to put the value of V2, that is omega 2 square R2 square by 2g. Okay, so this is the equation if it is situated on the point 1. Okay, so this is the equation. We can give some equation here, and this if you see the Z value, that is varying with the R because remaining things are constant. Omega is constant, G is constant, so only one term is there, that is R. So omega here varies with the square of R. Okay, and this, if you see this equation, suppose this is the equation 1 or something equation you give, and this equation actually it indicates the equation of a parabola, and this means that what? The free surface of the liquid, this free surface of the liquid, okay, is a paraboloid, okay. So I hope you understand the equation. The free surface of the liquid is shown as paraboloid. So I hope you understand this derivation. If you are having any kind of query regarding this or doubt regarding this, you can give a comment on the comment box. Thank you all.